right, AP Bio, welcome to our Hardy-Weinberg math skill quick presentation. And so again, let me turn off my music. So in this one, we're going to talk about Hardy-Weinberg, which is some of the math, which is one of the few math problems you have, or math skills that you have to do for the AP exam. And so what is Hardy-Weinberg theory? It's an equation that enables us to determine how much a population is evolving from generation to generation. And so what it is you look at an original number, a value, and then you check to see if that value has changed. And so this is the key point here. Hardy-Weinberg equilibrium refers to an ideal non-evolving population. And so if a population is in Hardy-Weinberg equilibrium, it's not evolving. In nature, really there are no populations that are in equilibrium. So here are the characteristics. So large size, so there's no genetic drift. Random mating, so there's no sexual selection. There's a stable environment, so no natural selection. No immigration or emigration, so there's no gene flow, and there's no mutations. And so really, there's no population Hardy-Weinberg equilibrium. And then if you remember the video, the 5 Fingers Evolution by Bozeman, right, those are populations that are evolving. And so if the question says, you know, a population is in Hardy-Weinberg equilibrium, it's not evolving. And so what you're doing is you're trying to look at a change from generation to generation. And so here's the equation. You have a formula sheet. And so for a trait controlled by 2 alleles, where P is dominant allele and Q is the recessive, your gene frequency, if they're talking about the gene frequency, that's P plus Q equals 1, right? And then if they're talking about the genotype frequency, that's P squared plus 2PQ plus Q squared equals 1. So if they're talking about like heterozygous, homozygous, the recessive, you're going to use that genotype frequency. If they're talking about the allele, that's like a P and a Q. So you got to be really careful, and we'll do some practice questions and those kind of things. So P plus Q equals 1 with the genotype frequency like P squared plus 2PQ plus Q squared equals 1. So kind of we'll do some practice with those. And so what this is showing you here, so the blue is the recessive, that's your Q squared. A, big A, little a, that's your heterozygous in green. And then big A, that's your red. That's your homozygous dominant. You can see over time as the P and the Q change, right? So as your Q is moving to 0, right? So there's no recessive alleles. Your dominant alleles are going up to being 100%. So these represents like percents. So if your P is 10%, your Q would be 90. It has to equal 1. So here's a sample problem, and this will probably be something we'll have to do. I'll have to do like another video on. But if a pea plant, the allele for purple flower is dominant to the allele for white. So purple would be your P. White would be your Q. If 99% of the plant's population have purple flowers, determine the percentage of heterozygotes in the population. And so that would tell you, so 0.99 is purple flowers. You know that your Q, right, must be 0.01. You can work from there. And again, I'll show you, I'll do a whole separate video on these. So when we talk about Hardy-Weinberg theory, it determines how populations evolve from generation to generation. It helps to determine which evolutionary pressures are affecting population more or less. So again, this is just a mathematical way to test or determine how a population is evolving. So this was a quick one. Again, I'll have supplemental videos for Hardy-Weinberg when we get to that point in class. So hopefully you found that helpful. I got to write down and make sure I get you guys your formula sheets. All right. So, hope you enjoyed this one. It's me signing off from 102 in the heart of beautiful Columbia High School on Tiffin Southside. Have a good one.